So welcome to the presentation of Wizards of DOS. We are the team from TU Darmstadt, from Germany, and our team is associated with the Chaos Computer Club in Darmstadt. And we have lots of members from the local university, which is how we got together. We basically got together 4 students and decided to participate in this competition. So that would be Alex, Florian, Nicolas, and me, Michael. So in terms of techniques, we solved most of the challenges with the fairly generic approach of using Ghidra and Python. So we simply used Ghidra in order to reverse engineer the binary, and oftentimes we had to write scripts that implement some functionality of the binary or implement attacks, and we did that by using Python. We also used OpenOCD for debugging. So we mostly dump the memory of the board as it is executing a challenge, and we set breakpoints at specific functions in order to compare the output with scripts or our emulator. So this emulator is a fork of librisc5, and we have added AFL support so that we can fuzz binaries. It sadly turned out that fuzzing is not a very useful technique for solving these challenges. And as a matter of fact, we didn't solve a single challenge by using fuzzing. However, this emulator also allows us to set breakpoints, and we can call arbitrary functions, which made it useful since other members could run the challenge binary without having access to the board. Then we also forked Anger, and the reason for that is that even though Anger has RISC-V support, it's in a very poor state. Even very basic instructions, such as the one that loads a single byte from memory into a register, contain bugs. And we tried to fix all of them and did a fairly good job at it. However, we ran into a new problem, and that is path state explosion. Basically, whenever Anger encounters a branch, it considers both possibilities, and this can result in many different states. In our case, so many states that we exhausted the memory of our host machine. And as a result, we weren't able to solve any challenges by using Anger directly. However, we did use its solver engine in order to solve one challenge. So we managed to solve most of the challenges. However, there are 4 exceptions. These would be Moon Landing, Hue, Corrupt, and Game. Now, in terms of the challenges that we solved, the first one would be Amnesia, which was fairly simple. You had to reset the board at the right moment so that the flash storage would be in the correct state, and then we could pass the challenge when the board started running the binary again. Breakfast was a binary we tried to solve by using fuzzing, but it didn't work out, so we resorted to manual reverse engineering. And it's basically a very simple crypto challenge. Burst is a challenge we tried to solve by using Anger, and that's where we encountered the state explosion. And we basically have to provide a number of integers which are checked against some arithmetic constraints. Float calculates the prime numbers up to a limit, and this limit can be bypassed by exploiting the parser for the string, since the parser doesn't check if the input is actually a digit. So we can input some special characters, which causes the parser to calculate a very big limit, and this allows us to trigger the watchdog and solve the challenge. Parthian was a classical cryptography challenge. In Chase, this is where armed randomness comes in. We have a linear congruential generator, and the modulus of the generator is around 18 bits, so we can actually brute force the states and see if a specific state would result in the system behaving in a manner which we have observed. And by doing this, we have a very low number of possibilities, and we can easily solve the challenge that way. SROM, which is the next challenge, was also a classical cryptography challenge. Then we have Middleman, where we had to forge an ECC signature. and the order of the generator is only around 8 bits, so we can easily brute force it in order to recover the private key and then sign the string that we auto sign. Sequence is a binary where we actually used our emulator to solve it. Chris required us to parse natural language and translate it into arithmetical expressions. There's actually a Python library which makes it very easy. And Recycle also uses a linear congruential generator, this time with a 32-bit modulus. However, the key is generated using only the lowest 8 bits, and this means that the state that we have essentially a generator with only an 8-bit state, and we can therefore solve the challenge. Virtual 1 and Virtual 2 used a virtual machine which we manually reverse engineered. Pursuit had some strings scattered around the binary, and we simply had to concatenate them in order to get a pass bin which contained the flag. And finally we have Impact, where we had to create a second pre-image attack on a custom collision function, on a custom hash function. And that's pretty much our presentation. Thank you very much for your time. I hope you enjoyed it.